Well, thank you so much for coming and for attending our talk. So as it was mentioned, with Bridgestone and QunaSys, we're going to talk about how to define a quantum computing strategy, how to think about, we've been hearing about this whole 2 days. So we're going to give a specific example of how Bridgestone has defined the strategy to tackle quantum computing and how us, QunaSys, have helped them to do that. So myself, I'm Elena Yndurain. I'm CEO for Europe, for QunaSys. QunaSys is a quantum computing software company. I'll tell a bit more about this. And I have joining me here Sato-san. He's the technology strategist in charge of the quantum computing program at Bridgestone. And we also have in the audience here Watanabe-san. He is the researcher at QunaSys, has been working in this project. So we're not going to be talking about algorithms or formulas. We're going to talk more about the journey. Okay, so we're going to, although we will give some examples of what is it that we're tackling and how we came to think about the use cases. So a bit about QunaSys, because some of you may not know us. So we are a quantum computing software company. It's a Japanese company, although we are expanding to the West, which is why I'm here. So our main product is a quantum computing chemistry software, an SDK that's available through the cloud. We'll talk about it a bit more today. Sato-san will explain how they used it integrated with regular chemistry software. So this software performs, it translates chemical properties into quantum algorithms. It's a simulator, but it can also be integrated with hardware. So we integrated with different hardware platforms, and it is also integrated with existing chemistry software so that chemists can use a familiar user interface. We do as well joint use case development. So we work together with companies to do either small proof of concepts, or we can do more advanced research, changing algorithms, updating algorithms. We have government subsidized projects, especially in Japan, with the Ministry of Innovation. We do run an ecosystem that's called QPark, which QPark stands for Quantum Practical Application Research Consortium. So it's a consortium of more than 50 companies in Japan, and now we're expanding it to global companies that they collaborate, they work together, and they learn quantum computing, and they keep up to date, and eventually they do some development as well. So it's 50 industry companies that are looking for practical use cases. We do co-branding events, like the one that was mentioned earlier by Yanni. So we hosted together last summer, the first Q2B in Tokyo. We also host some events in Europe with the Pistoia Alliance, more pharma. And we have open source material. So if you want to learn a bit quantum, we have an open textbook to learn quantum computing. We also have a benchmark tool that you can test the performance of the algorithms with different technologies, with different quantum hardware technologies. It's called Quantangle. And then we have the training courses. So we have training as part of QPark. We have training that we also do together with other institutions. So we did a recent training with the University of Strasbourg in October, a 1-week full training from the basics of quantum computing up to the coding and development of real use cases to test experts in physics or chemistry and how to develop quantum computing. So I'll let Sato-san talk about Bridgestone.
Okay, I'd like to introduce my company briefly. Bridgestone is one of the largest tire company in the world, and in addition to tire, we also provide a wide variety of diversified products, which includes industrial rubber and sporting goods. Our products are sold in over 150 nations and territories around the world. Today, our topic is focused on main products, tire. Tire looks like as black donuts, but the structure is more than complex, much more complex than it seems. You can see the basic structure of passenger tire on top left column, And this picture shows usual passenger tire is constructed with 5 main components. Each component has a different role in tire features, and various chemical reactions that occur in these components play a key role in tire performances. So I have been working on the analysis of these chemical reactions by using quantum chemical calculations. But I also have struggled with the limitation of calculations. One key issue is the balance of accuracy and computation cost. The more you want to get accurate results, the greater the computation cost. That's why I was curious about quantum computer. However, however, I was not a quantum native at that time, and I don't have any academic connection in this field, so I was at a loss as to how to approach this new paradigm. That's when I found QPark.
Okay, so Sato-san of Bridgestone decided to join QPark. As I was mentioning, QPark is a consortium that companies can join, and they have a membership of 1 year, and they have access to several educational tools, mainly to learn quantum computing, also the different lectures from experts to keep up to date and what are the latest trends that are happening in quantum computing from research to industry. We recently started adding international companies, so I think BMW in their talk already mentioned that they have joined QPark to start this collaboration. So companies can either, once they join QPark, they can decide, like Bridgestone, that they want to work together with us and define a strategy, or directly go and develop a use case, and some even collaborate between each other to develop, to think about algorithms and discuss and brainstorm and decide how to move forward. So when you join QPark, there is obviously a journey. We've all talked about this journey, of quantum computing journey. So we have 4 main steps, right? So we have first is getting the skills, and this, in the case of Bridgestone, was crucial, because Sato-san will talk a bit more about this. Once they learned the skills, they realized that they had to expand the scope of the use cases. We also help identify these use cases. So what are the different use cases they can work on? How do you prioritize these use cases? How well do each use case work with the current technology? Because as we have been hearing in the conference, the performance of a use case is gonna, so the performance of the hardware is one thing, but each use case is gonna work different with each of the hardware. So one of the things that we do is that we propose which hardware would work better for a specific use case. So you need to understand the use case together with the company, then translate it to the algorithm, and then see how that algorithm would work with a specific hardware. Then we test the algorithms, and then obviously we explore a bit more the technology. We'll talk about it in a couple of slides. How do you map the technology evolution with how your problem is going to be scaling? So right now we're doing small problems, but as the technology gets it works better, and we have more qubits and better quality, what type of problems are we going to be able to tackle? And that's what we do in that exploration of the technology. And all through the way, what we have is a collaboration of the ecosystem with academia, with government, with all the parties that we have in QPark. So QPark, we have a set of member companies, but we also have a set of partners that are sponsoring it. So we have all the hardware providers, we have government as well, and we even have as well like HPC companies that are working with us. So the training has, as I mentioned a bit earlier in this Strasbourg training, it has 2 parts: the concepts. So what is quantum computing? What is the basics of quantum information? But then we get in depth. What are the applications? How do they work? What is the length of of the circuit, the underlying circuit, what's the depth, how many qubits, and explore the capacity for each of the use cases. That's something that's valuable when you're deciding how to approach to manage the expectation of a technology.
Okay, one of the group work in QPark was reaction pathway search by using GRRM and CAMI. GRRM is an algorithm for automated exploration of chemical reaction pathways by utilizing energies obtained from quantum chemical calculations. Quantum chemical calculations, and this is the first time study connecting GRRM and quantum simulator. We tried to explore the isomerization reaction pathway of diazen, and we found interesting results. As you can see the results of root search for diazen, initial spin state of diazen is singlet, but final spin state of upper pathway is triplet. These results could never be obtained from conventional quantum chemical calculations. I was so excited because this result means we can search chemical reactions without any consumption about whether ionic or radical calculations. Radical reactions. I think this is a kind of advantage of quantum computer for chemical issues. Next, please. Convinced of the prospect of the quantum computer in chemical field, I decided to work with QunaSys to consider what value it could be bring to our company. And then HHA algorithms and optimizations were selected to define a quantum application roadmap. Yes, please. Many interviews were conducted with key engineers in my company, and potential use cases to explore are defined as summarized here. Entire design, they want to more precise modeling for FEM calculations, which has more than 10 times 8 degree of freedom. Entire manufacturing process, they want to optimize a huge amount of pattern with real-time update. This demand could be possible in FTQC era, so we have to prepare step by step. Next, please. In an initial effort to FTQC era in chemistry field, I'm currently conducting the reaction pathway search between oxygen and small molecules that makes up Thai materials. Oxidation reaction effort. Oxidation reaction is one of the reasons of degradation of Thai materials, and various reaction mechanisms were proposed from previous research. So I'm looking forward to unexpected reaction pathway. This slide is our quantum application roadmap. I won't go into details, but I had assumed more than 10 years from step 1 to step 3, but I feel the quantum computing technology advancing very quickly here in Q2B. So I'd like to start fundamental research immediately, especially for HHL algorithms.
So to wrap up, as you can see, what we did in the journey was, so Bridgestone had an original idea on what to test. They started talking to the experts as part of the QPAR collaboration, and one of the suggestions was, why don't you simulate your results? And this is why we did the integration with the GRRM for the reaction path search. And then why don't you expand the use cases? And you realized they could expand it more to chemistry calculation, HHL algorithms, and optimization. And then, of course, they learned how to code, and they did a lot of tests through Kami, and then they defined, as you see in the roadmap, how is a long-term roadmap going to look like. And although we're starting right now with this first example, how are we going to move forward to expand it? So we'd like to invite you to join QPark, and we have a specific group that focuses in HHL. So if you'd like to work on that specific calculations for structural calculation and heat and fluid simulations, we'd love to to have you there. Okay, well, thank you very much.
Okay, thank you to our speakers. We have time for one question. If
Yeah,
there's
sorry.
questions in the audience.
We're leaving, sorry about that.
Yes.
Sorry. I thought we were.
So you mentioned your experiment with diazine. Is there some particular element of quantum computation that made a difference? You said that you got better results. I mean, can you point to a specific reason for that?
The diazine, the test you did with diazine when you
we-
were testing the GRM integration.
We have many calculation results with conventional quantum chemical calculations, so we choose diazine. That's why.
Did you see any difference? The question is, when we did the test,
Difference.
in the test, any improvement with the...
Improvement. There's no improvement.
Yeah, so
Not similar. We use quantum simulator. We got triplet state. But in conventional quantum chemical calculations, if we set singlet state, calculation is leads to only singlet, not never triplet. So that's the advance, I think.
So the goal was to see if you can actually simulate it, and that's why we used the GRM integrated with Kami, and that was achieved.